All right, we're going to start with a little review of the different types of acceleration we have. So our first type, angular acceleration, has alpha. It's in radians per second squared. The next one we come across is linear acceleration. This is also known as the tangential acceleration and is in units of meters per second squared. And the third one is radial acceleration, sometimes referred to as centripetal acceleration, also in meters per second squared. Now what these three different accelerations tell me is different things. So alpha tells me about a change in angular velocity, both the magnitude and direction of that angular velocity. And angular velocity, you'll remember, is omega. Linear acceleration tells me about only the magnitude, tells me about the change in the magnitude of the velocity. Radial acceleration tells me about the change in direction of the velocity, and both of these again are linear velocity here. Over here you'll see the relationship. So tangential acceleration and angular acceleration are related by this equation. The linear acceleration or tangential acceleration is equal to alpha times r, the distance from the axis of rotation to the point experiencing the linear acceleration. The centripetal acceleration or the radial acceleration is equal to the linear speed squared divided by r, or omega squared times r. Okay. Now we're going to move into what happens when our torques are not balanced. We don't have an equilibrium situation, when the sum of the torques is not equal to 0. If it's not equal to 0, it's going to equal I times alpha, and we can then calculate out what is alpha going to be. And in turn, once we find alpha, we could find the linear acceleration of any point on that object that's rotating. So in order to sum up the torques, we are going to have to draw that free body diagram, just like we did in static equilibrium. Here's an example of one. And then for that I value, we're going to have to use one of those four methods we learned about just a while ago.